The sky above Crimea holds nothing unusual on the morning of August 30th, 2019. Gennady Borisov, an amateur astronomer with decades of patience, adjusts the focus on his custom-built telescope at the Margot Observatory. He photographs the same patch of darkness he photographed the night before. And the night before that, stars appear as points. Galaxies smear into faint ovals. Everything stays where it belongs, except for one thing, a dim speck. Magnitude 19, far too faint for human eyes, appears in a slightly different position than it occupied 24 hours earlier. This is normal. Asteroids do this. Comets do this. The solar system is full of moving things. But something about the motion feels wrong. Borisov measures the speck's position against the background stars. He calculates its apparent rate of travel across the sky. Then he checks the existing catalogues databases containing the predicted positions of every known asteroid, every known comet, every piece of orbital debris that humanity has catalogued over the past 2 centuries of systematic sky surveys. The speck is not in the catalogues. This, too, is normal. New objects are discovered constantly. But the direction of motion troubles him, the angle, the speed. He takes another image the following night. The speck has moved again, and now the wrongness becomes measurable. Within 72 hours, observers at other facilities confirm the object's existence and contribute their own measurements. The Minor Planet Center in Cambridge, Massachusetts, a clearinghouse for solar system discovery, receives the data and begins calculating a preliminary orbit. The numbers that emerge are strange. The orbit is not elliptical. It is not a closed loop around the Sun. Instead, the trajectory bends into a hyperbola, a shape that arrives from interstellar space, swings once around the Sun, and departs into interstellar space forever. The eccentricity of the orbit exceeds 3.0. Anything greater than 1.0 means the object is unbound from our star's gravity. This comet belongs to no sun. It is only visiting. The scientific community assigns it a designation 2I/Borisov. The 2I means second interstellar object. The first was discovered 2 years earlier, a different kind of visitor, more mysterious in some ways, less mysterious in others. But 2I/Borisov arrives with a visible coma, a halo of gas and dust, which marks it unmistakably as a comet. This is, in a way, comforting. Comets are understood, comets are predictable, except this one did not form in the cold outskirts of our solar system. It formed somewhere else, around another star, in another planetary nursery. And now it is here, moving through our neighbourhood for the first and only time in its existence, which may span billions of years. Only took 4.5 billion years for a comet from another star to show up exactly when humans had telescopes sensitive enough to spot it. Or perhaps they passed through before, in the Jurassic, in the Proterozoic, unseen and unrecorded. Or perhaps the sky has always been full of these visitors, and only now do we notice. The galaxy does not announce its traffic. It simply sends things through, indifferent to whether anyone watches. Borisov's telescope cost him years of careful construction. The discovery takes 3 nights. The comet itself takes 4 million years to cross the distance between stars, assuming it came from the nearest system, which it probably did not. Time operates on different scales depending on what is moving. For a human, 72 hours of uncertainty. For a comet, geological ages of silence and cold. The universe does not pause for observation. It continues. The speck continues. The sky continues. And somewhere in the data, a hyperbolic curve waits to be understood. The mathematics of celestial mechanics reduces motion to elegance. Every object moving under gravity follows a conic section circle, ellipse, parabola, or hyperbola. These shapes emerge naturally from Newton's equations, from the inverse square law that governs how masses attract across emptiness. For nearly every object in the solar system, The shape is an ellipse. Planets trace ellipses around the Sun. Moons trace ellipses around planets. Comets from the Oort cloud fall inward on elongated ellipses that take thousands or millions of years to complete, but they always return. The shape is closed. The orbit loops back on itself. Everything that belongs to the Sun is trapped in repetition. 2I/Borisov follows a hyperbola. Hyperbola is an open curve, has no far end. An object on a hyperbolic trajectory approaches from infinity, accelerates as it falls toward the Sun, whips around the central mass at perihelion, the point of closest approach, and then races back outward, decelerating but never stopping, never turning around, never returning. The object came from the space between stars and will return to the space between stars. It is passing through, not orbiting. The distinction is absolute. The mathematics allows no ambiguity. Astronomers calculate 2I/Borisov's orbital elements using positional data from dozens of observatories. The eccentricity settles at approximately 3.36. This number describes how stretched the orbit is, how far from circular. For context, Earth's eccentricity is 0.017, nearly a perfect circle. Halley's Comet, with its 76-year ellipse, has an eccentricity of 0.967, very stretched but still bound. Anything above 1.0 is unbound. At 3.362, I/Borisov is not even close to being captured. It is moving at roughly 33 kilometers per second relative to the Sun, far beyond escape velocity. Even if it wanted to stay, even if some force applied gentle braking over millions of years, the kinetic energy is too great. The comet will leave. The semi-major axis of the orbit, a parameter that describes the size of an ellipse, becomes meaningless for a hyperbola. Or rather, it becomes negative, a mathematical artifact indicating that no closed loop exists. Instead, astronomers focus on the incoming velocity vector, the point of perihelion, and the outgoing asymptote, the direction the comet will eventually travel after the Sun's gravity releases its grip. These calculations reveal that 2I/Borisov approached the solar system from the direction of the constellation Cassiopeia. Moving through the plane of the planets at a shallow angle, it will depart toward the constellation Telescopium, below the ecliptic, into the southern celestial hemisphere. The trajectory carries no memory of intention. There is no aim, no guidance. The comet arrives from a direction that happens to be roughly perpendicular to the plane of the Milky Way's disk, suggesting it may have been travelling through interstellar space for a long time, long enough that the original motion imparted by its home star system has been perturbed, randomized by distant gravitational influences, by the slow drift of stars through the galaxy's rotating structure. Or perhaps it was flung outward with exactly this velocity, this angle, billions of years ago, and has coasted through darkness ever since, untouched except by starlight and cosmic rays. Perihelion occurs on December 8, 2019, at a distance of roughly 2 astronomical units from the Sun, twice the distance between Earth and the Sun, just beyond the orbit of Mars. This is close enough for solar heating to sublimate the comet's ices, producing the coma and tail that make it visible, but not close enough to cause catastrophic disruption. Some comets, those that graze too near the Sun, fracture from thermal stress or tidal forces. 2I/Borisov remains intact. It rounds the Sun in a smooth arc, obeying gravity with the same indifference it has shown for eons. The speed of perihelion reaches approximately 44 kilometers per second. This is fast, but not extraordinarily so. Some long-period comets from the Oort cloud fall inward at similar speeds, though they slow down afterward, climbing back up the Sun's gravity well until they hover nearly motionless at the distant aphelion, thousands of astronomical units away, before beginning the long fall inward again. 2I/Borisov does not slow down enough to stop. It climbs the gravity well and simply keeps going. The Sun's influence fades. The velocity asymptotically approaches a constant value, the speed at which the comet will cruise through interstellar space for the next million years, or 10 million until it encounters another star, another gravity well, another brief perturbation. Only took humanity 400 years of telescopic astronomy to witness this. Or perhaps it happened before, many times, and no one calculated the orbit carefully enough to notice. The sky is full of faint things moving in unexpected ways. Most are never analysed. Most are recorded and forgotten. The universe does not require witnesses. It simply continues. The hyperbola continues. The mathematics continues. And somewhere in the equations, a comet traces a curve that opens toward infinity and never closes. Light carries information across distance. When sunlight strikes the surface of a comet, some photons absorb into the ice and dust, warming the material, breaking molecular bonds. Other photons scatter, reflecting back into space, carrying with them the fingerprint of whatever molecules they encountered. This scattered light, faint, red-shifted or blue-shifted, depending on the comet's motion, travels across millions of kilometers to Earth. Where telescopes gather it, spectrographs split it into component wavelengths, and detectors convert it into data. The data becomes a spectrum, a graph showing how much light arrives at each specific colour, each specific frequency. Every molecule absorbs and emits light at characteristic wavelengths. The spectrum is a chemical signature. It reveals composition without requiring a sample, without touching the object at all. Throughout late 2019 and early 2020, observatories around the world and in space point their instruments at 2I/Borisov. The Hubble Space Telescope, the Very Large Telescope in Chile, the Gemini Observatory, the ALMA radio array, dozens of facilities contribute observations, building a comprehensive spectral portrait of the comet as it moves through the inner solar system. The goal is to determine what this visitor is made of, to compare its chemistry to the comets that formed here, in our own protoplanetary disk, 4.5 billion years ago. The first detection is water. Specifically, hydroxyl radicals, OH molecules produced when ultraviolet sunlight breaks apart water molecules in the coma. The spectral lines appear at exactly the wavelengths expected for OH. This is unsurprising. Water ice is the primary component of most comets. Comets are often described as dirty snowballs. Though the ratio of ice to dust varies, what matters is that water is universal. It forms wherever hydrogen and oxygen exist in sufficient quantities at sufficiently low temperatures. Interstellar space is full of water ice, coating dust grains in molecular clouds. Protoplanetary disks are full of water ice, condensing beyond the frost line where temperatures drop below freezing. Every star system with rocky planets and icy bodies produces water. 2I/Borisov's water is not exotic. It is ordinary. It is the same molecule. But then the details emerge. Spectroscopic analysis reveals carbon monoxide CO in abundances higher than typically observed in solar system comets. Carbon monoxide ice is more volatile than water ice. It sublimates at much lower temperatures, around 25 Kelvin instead of water's 150 Kelvin. This means CO-rich ices can only survive if the comet formed in an extremely cold environment, far from its parent star, or if it spent most of its existence in interstellar space where temperatures hover just a few degrees above absolute zero. The presence of abundant carbon monoxide suggests 2I/Borisov formed in the outer regions of its home planetary system, analogous to our Kuiper belt or Oort cloud, and was ejected early, before the CO could sublimate away. Cyanogen CN also appears in the spectrum, along with traces of diatomic carbon C2. These are common in solar system comets. They form from the breakdown of more complex organic molecules under solar radiation. The ratios are slightly different from the average solar system comet, but within the range of natural variation. Some comets are CN-rich, some are CN-poor. The diversity reflects different formation conditions, different temperatures and pressures in different parts of the protoplanetary disk. 2I/Borisov fits within this diversity. It is not chemically alien, it is chemically familiar. A comet from another star looks like a comet from our star because the physics of comet formation is the same everywhere. Except for one mystery: measurements of the dust-to-gas ratio. The amount of solid particles relative to sublimating gases in the coma suggests 2I/Borisov is slightly more gas-rich than typical solar system comets. The dust production rate remains steady as the comet approaches perihelion, but the gas production increases more than expected. This could indicate a higher proportion of volatile ices, or a different internal structure, or simply observational uncertainty. The comet is far away, the coma is faint. Extracting precise ratios from noisy spectra requires careful calibration. The mystery is small, perhaps not a mystery at all, but it lingers in the data. Water from another star tastes the same as water from this star. Only took 4 billion years and 10 trillion kilometers for these molecules to arrive here. Unchanged, or perhaps changed in ways too subtle to detect. The spectrum reveals bulk composition, not isotopic ratios, not the fine details of molecular structure that might encode information about temperatures and pressures during formation. Those measurements require closer observation, better instruments, longer integration times. 2I/Borisov moves through perihelion and begins its outward journey before all the questions can be answered. The light it reflects grows fainter each week. The spectral lines dim into noise. And somewhere in the remaining data, a chemical signature waits, incomplete, a message written in wavelengths that no one will fully decode. 2 years earlier, on October 19, 2017, a different object passes through the inner solar system on a different hyperbolic trajectory. The Pan-STARRS telescope in Hawaii detects at first a faint point of light moving rapidly against the background stars. By the time astronomers calculate its orbit and realize what they are observing, the object has already rounded the Sun and begun its outward journey, accelerating away from Earth, receding into the darkness beyond Mars. There is no time for detailed study, no time for multiple observatories to coordinate long-exposure spectroscopy. The object is dim, distant, and departing. Observers gather what data they can in the brief window before it fades below detection threshold. The International Astronomical Union assigns it a designation 1/Oumuamua. The 1I means first interstellar object. The name comes from Hawaiian, meaning scout or messenger, the first arrival from a distant place. It is an appropriate name. Though the object carries no message, it simply moves. But the motion itself is strange. Initial observations suggest Oumuamua is elongated, perhaps 10 times longer than it is wide, shaped like a cigar or a needle or a shard. This shape is inferred from the way its brightness varies as it tumbles through space, rotating end over end every 7 to 8 hours. When the long axis points toward Earth, more surface area reflects sunlight, and the object appears brighter. When the narrow end points toward Earth, less area is visible, and it dims. The magnitude changes by a factor of 10, an unusually large variation, implying an unusually extreme shape. No asteroid or comet in the solar system has ever been observed with such an aspect ratio. The shape is not impossible. Tidal forces, collisions, or structural failure could produce elongated fragments. But it is uncommon. It is puzzling. Spectroscopic observations, limited by the object's faintness and rapid motion, reveal a reddish colour. The surface reflects light with a spectrum similar to some outer solar system objects' Kuiper belt bodies, trans-Neptunian objects that have been irradiated by cosmic rays for billions of years, organic compounds subjected to high-energy particles in the vacuum of space, darken and redden over time. This process is well understood. It is called space weathering. Oumuamua's colour suggests a surface that has been travelling through interstellar space for a very long time, bombarded by galactic cosmic rays, slowly altering its chemistry in the absence of any protective atmosphere. But then comes the anomaly. As astronomers refine Oumuamua's trajectory using weeks of positional data, they notice something unexpected. The object is accelerating very slightly, very gently away from the Sun. The acceleration is small, about 1/1,000,000th of a meter per second squared, but it is real, detectable, and directional. It points away from the Sun, as if the object is being pushed by some outward force. This is normal for comets. Comets accelerate away from the Sun due to outgassing when solar heat sublimates ices on the sunward side. The escaping gas acts like a tiny rocket engine, producing thrust. The effect is called non-gravitational acceleration. It is predictable, calculable, and always present in active comets, except Oumuamua shows no signs of outgassing, no coma, no tail, no spectral lines indicating the presence of water vapor, carbon monoxide, or any other volatile molecules escaping into space. Sensitive observations with Spitzer Space Telescope detect no infrared emission from dust grains, no thermal signature of sublimation. The object appears inert, inactive, asteroid-like, yet it accelerates as if it were outgassing. The discrepancy is small but persistent. The data does not resolve into a simple explanation. Several hypotheses emerge. Perhaps Oumuamua is outgassing something invisible pure nitrogen ice, or carbon monoxide in quantities too small to detect spectroscopically but sufficient to produce the observed acceleration. Perhaps the object is unusually light, with a very low density, making it more susceptible to radiation pressure from sunlight alone. Perhaps the shape is not cigar-like but flat, like a disc or a pancake, which would increase the surface area exposed to radiation pressure. Perhaps the internal structure is porous, like a fractal aggregate of smaller particles, with most of the volume occupied by empty space. Each hypothesis requires specific conditions that are plausible but not confirmed, not directly observed. The mystery does not resolve. Oumuamua fades from view in January 2018, too distant and too dim for further observation. It continues outward, past Jupiter, past Saturn, eventually crossing the orbit of Neptune and entering the space beyond, where the Sun's light dims to a point and interstellar darkness resumes. The acceleration continues, presumably, though no one can measure it anymore. The object tumbles through the void, carrying its unexplained motion, its strange shape, its reddish surface, into the galaxy. It will never return. It will never be observed again, and somewhere in the archived data, a small anomaly waits unresolved, annotated, filed under phenomena requiring further study. Only took 4 billion years for the first interstellar visitor to arrive exactly when humans were watching, but not quite ready to understand it. Or perhaps it makes perfect sense. And the strangeness is merely unfamiliarity. The universe contains multitudes of objects. Not all of them behave the same way. Not all of them fit existing categories. The sky does not pause for human comprehension. It simply continues. The hyperbola continues. And somewhere between the stars, Oumuamua continues, unobserved and unexplained. To see what moves requires patience and repetition. The human eye cannot detect motion in the night sky except for meteors, satellites, and the slow drift of planets over weeks. Everything else appears fixed. The stars hold their positions. The galaxies remain motionless. Even comets, racing through the solar system at tens of kilometers per second, appear as stationary points when observed for only a moment. Motion becomes visible only through comparison the same patch of sky photographed twice, hours or days apart. The image is overlaid and subtracted. Anything that has moved appears as a difference, a bright spot in one image and a dark spot in the other, or simply a new point of light where none existed before. Modern astronomy automates this process. Wide-field survey telescopes photograph vast sections of sky each night, covering hundreds or thousands of square degrees, recording the positions of millions of stars, galaxies, and solar system objects. Software compares each new image to previous images of the same region, flagging any changes, new objects, moving objects, transient events like supernovae or variable stars. The process is called difference imaging. It is how most asteroids are discovered. It is how comets are discovered. It is how Oumuamua and 2I/Borisov were discovered. The human role reduces to examining the flagged detections, confirming they are real and not artifacts, and initiating follow-up observations if the object seems unusual. But the sky is large, and most objects are faint. A comet at magnitude 19 like 2I/Borisov at discovery is roughly 100,000 times dimmer than the faintest star visible to the naked eye. Detecting such an object requires a telescope with substantial light-gathering power, a sensitive digital camera, and sufficient exposure time to accumulate enough photons for the comet to register above the noise level. Even then, the comet appears as a barely distinguishable smudge among millions of similar smudges, stars, galaxies, cosmic rays hitting the detector, hot pixels, red noise. Separating signal from noise requires statistical analysis, pattern recognition, and sometimes luck. The detection threshold determines what can be seen. Fainter telescopes miss fainter objects. Shorter exposures miss transient events. Surveys that revisit the same region of sky infrequently miss fast-moving objects that pass through between observations. The current generation of survey telescopes pan stars. The Catalina Sky Survey, Atlas scan the sky with varying cadences and sensitivities, optimized for different science goals. Pan-STARRS focuses on discovering potentially hazardous asteroids that might threaten Earth. Atlas focuses on detecting imminent impactors, objects only days or weeks from collision, requiring nightly scans of the entire visible sky. Neither system is optimized for finding interstellar objects, which are rare, faint, and unpredictable in their arrival direction. Yet both systems found one. The discovery of Oumuamua and 2I/Borisov was, in a sense, accidental. The objects happened to pass close enough to Earth, at the right time, moving slow enough across the sky to be captured by surveys designed for other purposes. If either comet had arrived a decade earlier, before Pan-STARRS and other modern surveys began operation, it would have passed unnoticed. If either had passed farther from Earth, beyond the detection threshold, it would have remained invisible. If either had moved faster across the sky, the motion blur would have smeared its image into undetectability. The discovery window is narrow, the probability is low, and yet it happened twice in 2 years. This suggests a population. If 2 interstellar objects pass through the inner solar system in 2 years, detectable by current surveys, then many more must be passing through undetected, either too faint, too fast, or arriving when no telescope was looking in that direction. Statistical models, extrapolating from 2 detections, estimate the density of interstellar objects in nearby space. The numbers vary depending on assumptions about size distribution, velocity distribution, and detection efficiency, but most estimates converge around 1 interstellar object larger than 100 meters in diameter, passing within 1 astronomical unit of the Sun every year. Smaller objects, too small to detect, must be far more numerous. The space between stars is not empty. It is full of exiles. Tracking a faint-moving object across multiple nights requires coordination. Once an object is detected and flagged as unusual, its position and motion are reported to the Minor Planet Center, which disseminates the information to observatories worldwide. Other telescopes, if they have time available, slew to the coordinates and attempt confirmation. Each additional observation refines the orbit, reducing uncertainty in the trajectory for interstellar objects. which move through the inner solar system quickly and do not return. This coordination is essential. There is no second chance. If the orbit is not determined accurately during the brief visibility window, the object is lost. Only took a century of photographic sky surveys, followed by decades of digital imaging, followed by years of automated difference imaging pipelines, to develop the capability to detect these visitors. Or perhaps the capability existed earlier, and no one looked at the data closely enough. The archives of old photographic plates, stored in observatory basements and climate-controlled vaults, contain millions of images of the sky dating back to the late 19th century. Some of those plates, if digitized and reanalyzed with modern software, might reveal faint streaks, comets or asteroids captured by accident, never followed up, never identified. Some of these streaks might correspond to interstellar objects. The universe does not wait for detection. It simply moves through. The motion continues. The algorithms continue. And somewhere in the data stream, a signal waits flagged, confirmed, reported, archived a record of something that came from elsewhere and will never return. A comet's coma is not solid. It is a cloud, a diffuse envelope of gas and dust surrounding the nucleus, the actual solid body at the centre. The nucleus itself is small, typically a few kilometres across, composed of water ice, carbon dioxide ice, carbon monoxide ice, and rocky or carbonaceous dust particles bound together in a loose, porous structure. When the comet is far from the Sun, beyond the orbit of Jupiter, the nucleus remains frozen and inert. Surface temperatures hover near the ambient temperature of interstellar space around 30 or 40 Kelvin. Nothing sublimates. The comet is dormant, invisible except by reflected sunlight, which at such distances is too faint to detect unless the nucleus is unusually large. As the comet approaches the Sun, solar radiation heats the surface. When the temperature rises above the sublimation point of the most volatile ice is carbon monoxide first, then carbon dioxide. Then water molecules break free from the solid lattice and escape into space as gas. This process, called outgassing, does not require melting. Ice transitions directly from solid to gas, bypassing the liquid phase. Because the surrounding pressure is nearly zero. In vacuum, sublimation occurs at much lower temperatures than it would on Earth. Water ice begins to sublimate around 150 Kelvin, far below the freezing point at atmospheric pressure. Carbon monoxide sublimates around 25 Kelvin, cold enough that even distant trans-Neptunian objects lose their CO over geological timescales. The escaping gas carries dust with it. Small particles, embedded in the ice, are lifted by the pressure of sublimating molecules and ejected from the nucleus at low velocities a few meters per second to a few hundred meters per second, depending on the volatile species and the local temperature. These particles, once freed, continue moving outward, no longer bound to the nucleus, forming a slowly expanding cloud. The gas molecules also continue outward, colliding occasionally with each other and with dust grains, but mostly travelling in straight lines away from the nucleus at thermal velocity speeds determined by the temperature of the gas, typically a few hundred meters per second. The coma grows as the comet approaches the Sun. At distances beyond 3 astronomical units, outgassing is minimal or absent. At 2 astronomical units roughly, where 2I/Borisov reached perihelion water ice sublimates vigorously, and the coma can extend hundreds of thousands of kilometers from the nucleus, larger in diameter than Jupiter but far less dense. The gas density in the coma is extraordinarily low, comparable to laboratory vacuums. A cubic meter of coma contains perhaps 1 million molecules, compared to the 10 to the 25th molecules in a cubic meter of Earth's atmosphere. By terrestrial standards, the coma is indistinguishable from empty space. Yet it is visible because the molecules scatter sunlight and because certain molecules like hydroxyl radicals cyanogen, and diatomic carbon fluoresce under ultraviolet radiation, absorbing high-energy photons and re-emitting them at visible wavelengths. Behind the comet, stretching away from the Sun, two tails form. The dust tail is composed of particles too large to be significantly affected by radiation pressure, but small enough to remain suspended in space rather than falling back to the nucleus. These particles follow independent orbits around the Sun, slightly perturbed from the comet's orbit by the initial outward velocity imparted during sublimation. Because they move slower than the comet, they lag behind, creating a curved tail that traces the comet's past trajectory. The dust tail glows by reflected sunlight. It is white or yellowish, broad and diffuse, sometimes spanning millions of kilometers. The ion tail is composed of ionized gas molecules that have lost electrons due to solar ultraviolet radiation and have become electrically charged. These ions are swept outward by the solar wind, the stream of charged particles flowing from the Sun's corona at speeds of 300 to 800 kilometers per second. The solar wind's magnetic field carries the ions directly away from the Sun, creating a straight, narrow tail that always points in the anti-solar direction, regardless of the comet's motion. The ion tail glows blue due to fluorescence of ionized carbon monoxide, which emits light at specific wavelengths in the blue part of the spectrum. The tail can extend tens of millions of kilometers, but its density is so low that stars remain visible through it without dimming. 2I/Borisov displays both tails, though faintly. Hubble images taken near perihelion show a bluish ion tail and a broader dust tail, similar in structure to solar system comets. The coma measures roughly 140,000 kilometers in diameter, large but not exceptional. The outgassing rate, estimated from the brightness of the coma and the spectral line intensities, suggests the nucleus is releasing several tens of kilograms of water per second, along with proportionally smaller amounts of carbon monoxide and other volatiles. This rate is consistent with a nucleus a few hundred meters to perhaps a kilometer across, though the exact size remains uncertain because the nucleus itself is too small and too deeply embedded in the coma to observe directly. The coma's glow is quiet, steady, predictable, no outbursts, no sudden brightening or fragmentation. Some comets, subjected to thermal stress or internal pressure from sublimating gases trapped beneath the surface, fracture into pieces. 2I/Borisov remains intact throughout its passage. The outgassing continues smoothly as the comet rounds the Sun and begins its outward journey. The coma gradually fades as solar heating decreases and sublimation slows. By late 2020, more than a year after perihelion, the comet dims below the detection threshold of most telescopes. The coma dissipates. The nucleus returns to dormancy. And somewhere beyond the orbit of Neptune, a small icy body continues outward, surrounded now by nothing but vacuum and darkness. The brief moment of visibility ended. The next encounter with stellar heat, perhaps a million years distant or never, only took a few months of sunlight to awaken ice that had been frozen for billions of years. Or perhaps it had been awake before, passing near other stars, briefly warming and outgassing in other planetary systems, then cooling again as it drifted back into interstellar night. The universe does not record these events, it simply allows them. The sublimation continues until the heat fades. The coma continues until the molecules disperse. And somewhere in the spectrum, a faint blue glow lingers, ionized carbon monoxide fluorescing in solar ultraviolet, a colour that has appeared around 1 trillion other stars, in 1 trillion other cometary comas, unremarkable and universal. Carbon monoxide freezes at 68 Kelvin under Earth's atmospheric pressure, but in the near vacuum of space, it remains solid at much lower temperatures down to around 25 Kelvin, the temperature at which thermal energy becomes sufficient for molecules to escape the ice lattice, even without external pressure. This is cold, interstellar space, far from any star. Hovers around 3 Kelvin, the temperature of the cosmic microwave background. the faint afterglow of the Big Bang, molecular clouds, the dense regions where stars form, reach temperatures between 10 and 50 Kelvin depending on density and proximity to young stars. Protoplanetary disks, the rotating disks of gas and dust surrounding newborn stars, exhibit temperature gradients hot near the star, cold in the outer regions, beyond the frost line, typically a few astronomical units from the star depending on its luminosity. Temperatures drop below 150 Kelvin, and water ice condenses, farther out, beyond 10 or 20 astronomical units. Temperatures drop below 50 Kelvin, and carbon dioxide ice becomes stable. Farther still, in the outermost reaches where giant planets form and icy planetesimals accumulate, temperatures approach 25 Kelvin, and carbon monoxide ice can survive. 2I/Borisov is rich in carbon monoxide. Spectroscopic measurements indicate CO abundance ratios higher than the solar system average for comets. Most comets observed from Earth contain water as their dominant volatile, with carbon monoxide present but subordinate perhaps a few percent by number of molecules. 2I/Borisov shows CO to water ratios closer to 1:1 in some observations, though measurements vary depending on which part of the coma is sampled and at what distance from the Sun. High carbon monoxide content suggests formation in a particularly cold environment, or prolonged storage at low temperatures, or both. This chemical signature encodes information about the comet's birthplace. If 2I/Borisov formed close to its parent star, where temperatures were too high for CO ice to condense, it would not contain much carbon monoxide. If it formed at intermediate distances, analogous to the asteroid belt or the Kuiper belt in our solar system, it might contain water and carbon dioxide but less CO. If it formed far from its parent star, in the cold outer regions analogous to our Oort cloud, or if it was ejected early and spent billions of years in interstellar space where temperatures never exceeded 25 Kelvin, then carbon monoxide ice could accumulate and persist. The presence of CO does not pinpoint the origin, but it constrains the possibilities. The comet comes from somewhere cold. Organic molecules also appear in the spectrum, though indirectly. Cyanogen CN and diatomic carbon C2 are fragments, daughter molecules produced when larger organic compounds break apart under ultraviolet radiation. The parent molecules might be hydrogen cyanide, acetylene, polyaromatic hydrocarbons, or more complex carbon chains. These compounds form in protoplanetary disks through gas phase chemistry and surface reactions on ice-coated dust grains. They're common in the outer solar system and in interstellar space. Comets from the Oort cloud often show similar organic signatures. The chemistry is universal. Carbon bonds to hydrogen, nitrogen, oxygen, and other carbons in predictable ways governed by quantum mechanics. The molecules that form around one star resemble the molecules that form around another star because the underlying physics is identical. Yet small differences exist. Some solar system comets are depleted in certain volatiles. Nitrogen, for instance, appears less abundant than expected based on cosmic elemental ratios. Some are enriched in deuterium, the heavy isotope of hydrogen, suggesting formation from interstellar ice that was enriched in deuterium through low-temperature chemical reactions in molecular clouds. These isotopic and elemental variations reflect local conditions during formation temperature, pressure, radiation environment, the mix of available elements. 2I/Borisov's composition is not identical to any single solar system comet, but it falls within the observed range of diversity. It is familiar but not quite the same, like a word spoken with a slight accent, recognizable but distinctly foreign. One mystery persists in the measurements, the dust-to-gas ratio, the proportion of solid particles to volatile molecules in the coma, appears slightly lower than typical solar system comets. This means 2I/Borisov produces more gas relative to dust, or equivalently, the nucleus contains a higher fraction of ices and a lower fraction of rocky or carbonaceous material. This could indicate formation in a region of the protoplanetary disk where ice is condensed more efficiently, or it could reflect the original composition of the molecular cloud from which the parent star system formed. Or it could be measurement error. Determining the dust-to-gas ratio requires comparing the brightness of the dust continuum light reflected by particles to the intensity of emission lines from gas. Both measurements are uncertain. The comet is faint. The signal is noisy. Different instruments, different calibration methods, different assumptions about particle sizes and gas temperatures yield different results. The carbon monoxide continues to sublimate as long as sunlight heats the surface. Each molecule, freed from the ice lattice, accelerates outward at roughly 500 meters per second, the thermal velocity corresponding to the temperature of the gas just above the nucleus surface. The molecule may collide with other molecules or with dust particles in the dense inner coma, transferring momentum, scattering in a new direction. Or it may escape collision-free, travelling in a straight line away from the nucleus, gradually becoming part of the diffuse outer coma. Eventually, some molecules are ionized by solar ultraviolet radiation, losing electrons and becoming susceptible to the solar wind's magnetic field, which sweeps them into the ion tail. Others remain neutral, drifting outward until they dissociate broken apart by photons or simply disperse into the general population of molecules in interstellar space. Only took 4 billion years for these molecules to freeze, travel between stars, and sublimate in the light of a sun they were never born around. Or perhaps they sublimated many times before, in earlier encounters, and refroze in the darkness afterward. Carbon monoxide does not remember its history. It simply transitions from solid to gas when temperature permits, and from gas to solid when temperature drops. The chemistry continues, the sublimation continues, and somewhere in the outflowing gas, a molecule drifts intact, unremarkable, carrying no information except the temperature at which it was released and the direction it happened to travel. One molecule among trillions, indistinguishable from the molecules that sublimate from solar system comets, identical in every measurable way except origin. Colour is a property of surfaces, not of objects themselves. What appears red or blue or grey depends on which wavelengths of light the surface absorbs and which it reflects. A surface that absorbs blue and green light while reflecting red light appears red. A surface that absorbs all wavelengths equally appears grey. A surface that absorbs nothing and reflects everything appears white. Though true white surfaces are rare in nature, most surfaces, especially in space, absorb some wavelengths preferentially, creating a spectral signature that reveals composition, texture, and history. 2I/Borisov's nucleus, the solid body beneath the coma, cannot be observed directly because the surrounding gas and dust are too bright, too diffuse, obscuring the central object. But the dust particles ejected from the nucleus can be analysed. These particles scatter sunlight, and the colour of the scattered light provides information about the particle's composition and size. Photometric observations, comparing brightness at different wavelengths, indicate the dust is slightly red, meaning it reflects more light at longer wavelengths, in the red and near-infrared part of the spectrum, than at shorter wavelengths in the blue. This is typical of cometary dust. The reddish colour suggests the presence of organic compounds, carbon-rich molecules that have been processed by radiation. Space weathering is a slow process. Cosmic rays, high-energy protons and atomic nuclei, accelerated by supernova shockwaves, active galactic nuclei, and other violent astrophysical events permeate the galaxy. These particles travel at nearly the speed of light, carrying energies millions of times greater than the thermal energy of ordinary matter. When a cosmic ray strikes a surface in space, it penetrates micrometers into the material, ionizing atoms, breaking chemical bonds, creating defects in the crystal lattice. Over millions of years, this bombardment alters surface chemistry. Organic molecules, originally pale or colourless, darken and redden as their structures become more complex, more polymerized, less volatile. The process is called irradiation darkening. It affects all objects exposed to space for geological timescales. Interstellar space has no shelter. A comet travelling between stars is exposed to the full intensity of galactic cosmic rays without the protective influence of a stellar wind or magnetic field. Solar wind, when present, partially deflects low-energy cosmic rays, reducing the radiation dose on objects within a few astronomical units of a star. But in interstellar space, there is no such protection. The radiation is constant, isotropic, relentless. A comet nucleus drifting through the galaxy for 1 million years, or 10 million, accumulates a radiation dose far exceeding what it would receive orbiting a star. The surface darkens, the organic compounds polymerize into complex, amorphous carbon structures tholins, the name given to the reddish-brown organic residues produced by irradiation of simple ices and hydrocarbons in laboratory simulations. The colour of 2I/Borisov's dust is consistent with this history. The reddish hue matches the colour of Kuiper belt objects, centaurs, and other outer solar system bodies that have been exposed to cosmic rays for billions of years. It also matches the colour of Oumuamua, the first interstellar visitor, which displayed a similar reddish spectrum. This similarity suggests a common process irradiation in interstellar space, affecting all objects that travel between stars. Regardless of their origin or composition, the galaxy imposes a uniform patina on its wanderers, yet the exact shade of red varies. Some objects are neutral grey, some are deep red, almost rust-coloured. The variation depends on the original composition, how much organic material is present to begin with, and the radiation dose, which depends on travel time and trajectory through the galaxy. A comet ejected from its home system 1 million years ago will have a different surface colour than one ejected 1 billion years ago. A comet that passed through a dense molecular cloud, shielded temporarily from cosmic rays by intervening gas, may retain a less weathered surface. A comet that collided with another object during its interstellar journey, exposing fresh, unweathered material, may show colour heterogeneity, red in some areas, grey in others. 2I/Borisov's colour is measured by comparing its brightness in different filters, optical wavelengths, near-infrared wavelengths. The measurements yield colour indices, numerical values that quantify how red or blue the object is relative to the Sun or to a standard star. The typical metric is the BV colour, comparing blue magnitude to visual magnitude, or the VR colour, comparing visual to red. 2I/Borisov's colour indices place it in the moderately red category, similar to the median solar system comet but slightly redder. The nucleus itself, hidden beneath the coma, may be redder still. Dust ejected from the surface likely samples the outermost layer, which may be more weathered than the interior. Fresh ice and organics, buried beneath a thin irradiated crust, remain pristine, unweathered, preserving the original chemistry from the comet's formation 4.5 billion years ago. Photometry alone cannot distinguish between weathering and composition. A red colour could indicate irradiated organics, or it could indicate iron-rich minerals, or it could indicate a mixture of both. Spectroscopy, measuring absorption features at specific wavelengths, provides more detailed information, but the comet's coma complicates spectroscopic observations. Emission lines from gas overwhelm the continuum, making it difficult to isolate the dust's reflectance spectrum. The nucleus remains unobserved, its true colour unknown, inferred only from the statistical properties of the ejected dust and the general trends observed in other comets. Only took a few million years of cosmic ray exposure to darken the surface to the point where it reflects most strongly in red light instead of blue. Or perhaps it was always red, formed from reddish material in a protoplanetary disk rich in organics. The colour does not reveal its own origin, it simply exists, a property measured by instruments, recorded in data tables compared to other measurements. The reddish hue continues to reflect sunlight even as the comet recedes. The organic compounds continue to absorb blue wavelengths and scatter red. And somewhere in the spectrum, a subtle gradient of colour persists a record of time, radiation, and the slow alteration of matter in the void, indistinguishable from 1,000 other red objects drifting through the galaxy. Remarkable only in that this one, briefly, passed close enough to be seen. Planetary systems do not hold all their material. During formation, as the protoplanetary disk collapses and planets coalesce from dust and gas, gravitational interactions scatter smaller bodies, planetesimals, embryos, comets, asteroids onto chaotic orbits. Some collide with growing planets, adding mass. Some fall into the star, vaporizing. Some achieve stable orbits in the asteroid belt or Kuiper belt, surviving for billions of years, and some are ejected entirely, flung outward at velocities exceeding the star system's escape velocity, becoming interstellar objects. This ejection is not rare. It is inevitable. Every planetary system produces exiles. The mechanism is gravitational scattering. When a small body passes close to a massive planet, Jupiter, Saturn, a gas giant in another system, the planet's gravity deflects the body's trajectory. If the encounter geometry is favourable, the deflection adds velocity in the direction of the body's motion, accelerating it. This process is called a gravity assist or slingshot. Space agencies use it deliberately to send probes to the outer solar system, using Jupiter's gravity to boost spacecraft velocity without expending fuel. But in a young planetary system, where thousands of planetesimals orbit chaotically, crossing paths with giant planets repeatedly, gravity assists occur randomly and frequently. Most encounters remove energy, causing the body to fall toward the inner system or settle into a more circular orbit. But some encounters add energy, boosting the body outward. A single encounter rarely provides enough velocity to escape the star system. Escape velocity from the Sun's gravity at Jupiter's distance is approximately 18 kilometers per second. Most planetesimals orbit at speeds around 13 kilometers per second, so they need an additional 5 kilometers per second to escape. A close encounter with Jupiter can provide several kilometers per second of velocity change, but usually not enough for immediate ejection. Instead, the body is kicked into a highly elliptical orbit, perhaps with an aphelion beyond Neptune's orbit, where it may encounter Saturn, Uranus, or Neptune on subsequent passes. Each encounter perturbs the orbit further. Eventually, after multiple scatterings, some small fraction of bodies accumulate enough velocity to leave the system entirely. Computer simulations of planetary formation model this process. The simulations begin with a protoplanetary disk containing thousands or millions of bodies ranging from kilometer-sized planetesimals to moon-sized embryos. Gravity is calculated between all bodies, along with collisions, fragmentation, and accretion. The simulations run forward in time, integrating the equations of motion over millions of simulated years. The results consistently show that for every planet that forms, 10 to 100 times more mass is ejected than retained in the final planetary system. Jupiter, for instance, likely ejected several Earth masses worth of material during its formation. Most of this material was scattered inward and consumed by the Sun, but a significant fraction, perhaps 10 to 20%, was scattered outward, achieving escape velocity, becoming interstellar comets and asteroids. The ejected bodies carry velocity vectors that depend on the details of their final scattering event. Some leave slowly, barely exceeding escape velocity, coasting outward at 20 kilometers per second relative to the star. Others leave faster, flung by particularly violent encounters with massive planets, reaching velocities of 40 or 50 kilometers per second. These velocities are measured relative to the star system they left. But the star itself is moving through the galaxy, orbiting the galactic center at roughly 230 kilometers per second in the case of the Sun. The ejected body inherits this motion. Its velocity relative to the galaxy is the vector sum of its ejection velocity and its parent star's orbital velocity around the galaxy. The result is a trajectory that does not point directly away from the parent star, but instead reflects the motion of the entire system through galactic space. Once ejected, the body becomes a rogue unbound from any star, drifting through interstellar space under the influence of galactic gravity alone. The Milky Way's gravitational field is weak at the scale of individual objects. There is no significant acceleration, no tidal forces strong enough to alter the trajectory over short timescales. The body coasts. Its velocity remains nearly constant, decreasing very slightly due to gravitational interactions with distant stars, perturbations too small to measure but cumulative over millions of years. Eventually, the body's trajectory may carry it near another star system. If the approach is close enough, the star's gravity captures the body temporarily, bending its trajectory into a hyperbolic arc, then releasing it back into interstellar space. This is what happened with Oumuamua and 2I/Borisov. They approached the Sun, swung around and departed. Most ejected bodies never encounter another star. The galaxy is vast, and stars are separated by light years of empty space. The probability of a close encounter within a few astronomical units is extremely low. A typical ejected comet might travel for hundreds of millions of years, or billions, without passing near any star. It simply drifts, cooling to the ambient temperature of interstellar space, its surface darkening under cosmic ray bombardment, its trajectory slowly perturbed by the galaxy's overall gravitational structure. Some bodies eventually fall back toward the galactic plane if they were ejected perpendicular to it. Some spiral inward or outward depending on their initial velocity and direction. Most continue indefinitely, neither falling nor escaping, part of the galaxy's distributed mass, the dark, cold population of rogue planets, comets, and asteroids that contribute to the total inventory of matter but never participate in planetary systems again. Only took a few million years of chaotic scattering to eject enough material from the solar system to populate interstellar space with trillions of comets. Or perhaps it took longer, 100 million years, with ejections continuing even after the planet stabilized, driven by slower processes like resonant perturbations and long-term orbital evolution. The galaxy does not account for its rogues, it simply releases them. The ejection continues, even now, at a much reduced rate as the solar system's remaining small bodies are gradually cleared by planetary gravity. And somewhere in the outskirts, beyond Neptune, another comet drifts toward an encounter with a distant giant planet. An encounter that will alter its orbit, perhaps sending it inward toward the Sun, perhaps outward into interstellar darkness. Another exile joining the silent multitude. The space between stars is not empty. It contains gas, primarily hydrogen and helium. The remnants of the Big Bang, mixed with heavier elements synthesized in stars and dispersed by supernova explosions. It contains dust, microscopic grains of silicates, carbon and ice, formed in stellar atmospheres and planetary nebulae. It contains magnetic fields, threading through the gas, influencing the motion of charged particles. It contains cosmic rays, photons, neutrinos, and it contains solid objects, planets ejected from their home systems, brown dwarfs that never ignited fusion, asteroids, comets. These objects are dark, invisible except when they pass close to a star and reflect its light. They drift silently through the galaxy, a distributed population of exiles, numbering in the trillions or quadrillions depending on how the calculation is performed. Estimating the population requires extrapolation from limited data. 2 interstellar objects detected in 2 years, combined with knowledge of survey sensitivity and sky coverage, provide a statistical baseline. Surveys like Pan-STARRS cover roughly 3/4 of the sky accessible from Hawaii, detecting objects down to magnitude 20 or fainter, depending on exposure time and atmospheric conditions. The detection of Oumuamua and 2I/Borisov implies that objects of their size a few hundred meters pass within 1 astronomical unit of the Sun, roughly once per year on average. Smaller objects, harder to detect, must be more numerous. Larger objects, easier to detect but rarer, must be less numerous. The size distribution follows a power law, similar to the distribution of asteroids and comets in the solar system. For every object 1 kilometer in diameter, there are roughly 10 objects half a kilometer across, 100 objects a quarter kilometer across, and so on. The exact exponent of the power law is uncertain, but typical values range between -2 and -3, meaning the number of objects increases steeply as size decreases. Integrating this distribution over all sizes yields an estimate of the total number of interstellar objects in a given volume of space. The result, for the solar neighborhood within a few light-years of the Sun, ranges from tens of thousands to hundreds of thousands of objects larger than 100 meters, depending on assumptions. Scaling this to the entire galaxy produces staggering numbers. The Milky Way contains roughly 200 billion stars, spread across a disk 100,000 light-years in diameter. If each star system ejected material during formation at rates similar to our solar system, and if the ejected material has been accumulating in interstellar space for billions of years, then the total population of rogue objects in the galaxy may number in the quadrillions, 10 to the 15th or even 10 to the 16th. Most of these are small, less than a kilometer across, invisible unless they pass very close to a star and observer, but collectively they represent a significant reservoir of mass, perhaps comparable to the mass contained in all the planets of all the star systems combined. This population is not uniformly distributed. Interstellar objects retain the orbital velocities of their parent stars around the galactic center. Stars in the thin disk of the galaxy orbit at roughly 200 to 250 kilometers per second. Stars in the thick disk, an older population, have more random velocities with a broader distribution. Stars in the galactic halo move on highly eccentric orbits with velocities that can exceed 300 kilometers per second relative to the disk. Objects ejected from these different stellar populations inherit different velocity distributions, creating a complex kinematic structure in interstellar space. Near the Sun, which orbits in the galactic disk, most interstellar objects are also moving with disk-like velocities, but a fraction come from the thick disk or halo, arriving at higher relative speeds. The density of interstellar objects varies with location. Near the galactic center, where stars are more densely packed, ejection events are more frequent, and the accumulated population is higher. In the spiral arms, where star formation is active, young planetary systems are currently ejecting material, adding to the population. In the regions between spiral arms, where star formation ceased long ago, the population consists only of old rogues, objects ejected billions of years ago, still drifting. The Sun is located between two spiral arms in a relatively quiet region, so the local density of interstellar objects is probably typical or slightly below average for the galactic disk. Detection rates depend on the object's trajectories relative to the solar system, an object moving perpendicular to the ecliptic plane. The plane in which Earth and the planets orbit spends less time near the Sun and is harder to detect. An object moving in the plane of the ecliptic, approaching from the direction of Earth's motion around the Sun, has a higher relative velocity and passes through the inner solar system more quickly, reducing the observation window. An object approaching from behind, in the same direction as Earth's orbital motion, has a lower relative velocity and remains visible longer, increasing the probability of detection. The geometry matters. Two objects with identical size and trajectory can have very different detection probabilities depending solely on their approach direction. Future surveys will improve detection rates. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s CES with a wide-field camera capable of imaging the entire visible sky every few nights down to magnitude 24 or fainter. This represents a sensitivity improvement of several orders of magnitude compared to current surveys. Models predict that Rubin Observatory will detect dozens of interstellar objects per year, possibly hundreds, depending on the actual population density and size distribution. This will transform the field from a curiosity to objects detected by chance into a statistical science, with enough detections to constrain formation models, chemical composition distributions, and the history of planetary system evolution across the galaxy. Only took 4 billion years for the galaxy to fill itself with exiles, and another few billion for humans to develop the instruments to notice them. Or perhaps it happened faster, in the first billion years, when star formation rates were higher and planetary systems formed in greater numbers. The galaxy does not catalogue its rogues, it simply accumulates them. The population continues to grow slowly, as new star systems form and new giant planets scatter, new planetesimals into interstellar darkness. And somewhere in the spiral arms, another comet leaves its home, accelerating past escape velocity, joining the silent census one more object among quadrillions, indistinguishable, unremarkable, drifting. The search for extraterrestrial intelligence SETI operates on the assumption that advanced civilizations, if they exist, might produce detectable signals, radio transmissions, laser pulses, waste heat from megastructures, atmospheric signatures of industrial pollution. These are the targets SETI searches for, scanning the sky with radio telescopes and optical instruments, looking for patterns that cannot be explained by natural astrophysical processes. The search has continued for more than 60 years. No confirmed signals have been detected. The galaxy remains silent, or humanity lacks the sensitivity to hear it, or the signals are not being transmitted, or they use technologies and frequencies beyond current detection capabilities. The Fermi paradox encapsulates this silence. If intelligent life is common, where is everyone? When Oumuamua was discovered in 2017, its unusual properties, the elongated shape, the non-gravitational acceleration, the lack of visible outgassing prompted speculation. Perhaps it was not a natural object. Perhaps it was a probe, a derelict spacecraft, a light sail pushed by radiation pressure from a distant laser. The speculation was not entirely unreasonable. An artificial object would move differently than a natural one. It might have a reflective surface optimized for radiation pressure. It might tumble in ways consistent with structural failure or deliberate spin stabilization. It might be elongated if it were a communication antenna or a structural truss. The idea, while unlikely, was testable. The Breakthrough Listen project, a SETI initiative funded by private donors, directed radio telescopes at Oumuamua in December 2017, scanning for signals across a wide range of frequencies. The observations covered the 1 to 12 GHz band, the region of the electromagnetic spectrum where radio waves penetrate Earth's atmosphere with minimal absorption and where many human-made transmissions occur. The telescopes listened for hours, collecting data as Oumuamua receded past the orbit of Jupiter. The data was processed, searched for narrow band signals, modulated signals, pulsed signals, anything that might indicate artificial origin. Nothing was detected. The object emitted no radio waves distinguishable from background noise. If it was a probe, it was silent. If it was natural, the silence was expected. 2I/Borisov, discovered 2 years later, prompted no such speculation. Its coma and tail marked it unambiguously as a comet. Outgassing explained the visible activity. The chemical composition matched cometary norms. The trajectory was consistent with gravitational dynamics. There was no anomaly requiring exotic explanations. No radio observations were conducted, or if they were, no results were published. The object was scientifically interesting but not mysterious. It fit within the framework of understood phenomena. Nature alone sculpts comets. No intelligence is required. The absence of artificial objects among interstellar visitors is not surprising. If intelligent civilizations exist and build interstellar probes, the probes would be rare compared to natural ejecta. Every star system produces trillions of comets and asteroids through gravitational scattering. Even prolific civilizations, launching thousands of probes, would contribute negligibly to the total population of interstellar objects. The probability of detecting an artificial object before detecting thousands of natural ones is vanishingly small. Unless the probes are designed to be conspicuous, brightly reflective, actively transmitting, deliberately approaching inhabited star systems, they would be indistinguishable from asteroids and ignored. Moreover, interstellar probes face significant challenges. Travel time between stars, even at relativistic velocities, spans centuries or millennia. Probes would need power sources lasting thousands of years, radiation shielding, self-repair mechanisms, and some form of intelligence or programming to respond to unexpected conditions. They would need to decelerate upon reaching a target system, which requires carrying fuel or using advanced propulsion techniques like magnetic sails. They would need to transmit data back to their origin, across light years, with enough power to be detectable. The engineering is formidable. Chemical rockets are insufficient. Nuclear propulsion might work but requires enormous fuel mass. Light sails, pushed by lasers, could achieve high velocities but cannot decelerate without a second laser at the destination. The obstacles are not insurmountable, but they are substantial. Natural processes require no engineering. Gravitational scattering operates automatically, ejecting material from every planetary system without intent or design. The galaxy fills itself with rogues through the ordinary dynamics of planet formation. These objects carry no messages. They transmit no signals. They are debris, remnants, the byproducts of accretion and scattering shaped by gravity and thermodynamics. They move through interstellar space not because they were sent, but because they were discarded. There is no purpose, no destination, no mission profile. They drift until they encounter another star or another object, or simply continue drifting indefinitely. Oumuamua's anomaly is the acceleration. The shape remain unexplained but are not inexplicable. Outgassing of a volatile species too faint to detect spectroscopically could account for the acceleration. A highly porous structure, with density low enough to increase sensitivity to radiation pressure, could account for the motion without requiring exotic materials. The shape could be a statistical outlier, rare but not impossible. The hypothesis that Oumuamua is artificial is not disproven, but it is unnecessary. Natural explanations, though incomplete, are sufficient. Occam's razor favours simplicity. The universe contains countless strange objects. Most of them are natural. Only took 2 interstellar objects to revive speculation about alien probes, despite 4 billion years of planetary formation producing quadrillions of natural candidates. Or perhaps the speculation never needed revival. It is a persistent human tendency to look for intention in randomness, design in debris, messages in the motion of rocks. The galaxy does not send messages through its ejector. It simply releases them. The silence continues. The search continues. And somewhere in the radio spectrum, telescopes listen to the void, hearing only noise, thermal radiation, synchrotron emission, the faint hiss of hydrogen spin transitions, nothing that requires intelligence to produce, nothing that suggests anyone is watching back. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, sits atop Cerro Pachon in northern Chile, 2,700 meters above sea level, where the atmosphere is thin and the seeing conditions are among the best on Earth. The observatory houses an 8.4-meter primary mirror and a 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy. The design is optimized for wide-field surveys, imaging large sections of sky in a single exposure rather than focusing on individual objects. Each image covers approximately 9 square degrees, roughly 40 times the area of the full moon. The entire visible sky from Chile, roughly 18,000 square degrees, can be photographed every 3 nights. Construction began in 2015. First light is anticipated in the mid-2020s, followed by the start of the Legacy Survey of Space and Time, LSST, a 10-year program to repeatedly image the sky, creating a time-lapse record of everything that changes. The survey will detect supernovae, variable stars, asteroids, comets, transiting exoplanets, gravitational lensing events, and any other transient or moving phenomena bright enough to register above the detection threshold of magnitude 24. This sensitivity is roughly 60 times deeper than pan-stars, meaning objects 60 times fainter can be detected. For interstellar objects, this translates to detecting smaller bodies at greater distances, expanding the observable volume of space and increasing the detection rate. Current estimates, based on the detection of Oumuamua and 2I/Borisov and extrapolations from population models, suggest that Rubin Observatory will detect between 1 and several dozen interstellar objects per year. The exact number depends on the true density of these objects in nearby space, their size distribution, and their velocity distribution relative to the solar system. If the population is denser than current models predict, the detection rate could reach hundreds per year. If the size distribution includes more large objects than expected, the rate increases because larger objects are easier to detect. If most interstellar objects approach the solar system at high velocities, perpendicular to the ecliptic, they spend less time in the detectable zone and the rate decreases. The uncertainty is large, but the improvement over current capabilities is unambiguous. Detecting an interstellar object is only the first step. Once detected, the object must be tracked to determine its orbit, observed spectroscopically to measure composition, and monitored photometrically to study variability and rotation. For objects passing through the inner solar system quickly, this requires rapid coordination among multiple observatories. Rubin will provide discovery alerts within 60 seconds of detecting a candidate object, distributing the data to the global astronomical community through automated systems. Follow-up telescopes, those equipped with spectrographs or high-resolution images, can then prioritize targets based on scientific interest. Interstellar objects, once confirmed, will trigger intensive observing campaigns, similar to the response to Oumuamua and 2I/Borisov, but more organized, more prepared. The scientific goals of studying interstellar objects extend beyond mere detection. Each object is a sample from another planetary system, carrying information about conditions in that system billions of years ago. Chemical composition reveals the temperature and pressure regime where the object formed. Isotopic ratios encode details about the molecular cloud from which the parent star condensed. Surface properties, color, albedo, texture record the history of space weathering during interstellar transit. Shape and rotation state provide clues about collisional history, tidal encounters, or fragmentation events. Collectively, a large sample of interstellar objects allows statistical analysis of planetary system formation across the galaxy, comparing the chemistry and dynamics of other systems to our own. Some objects may originate from very distant stars, ejected billions of years ago when the galaxy was younger and star formation rates were higher. These ancient wanderers carry information about the early galaxy, before the sun formed, before the solar system existed. Their chemistry reflects the metallicity of the interstellar medium at the time their parent stars formed the abundance of elements heavier than hydrogen and helium. which increases over cosmic time as successive generations of stars synthesize and disperse heavy elements through supernovae. Measuring this chemistry, comparing it to solar system abundances, constrains models of galactic chemical evolution. Other objects may originate from nearby stars, ejected recently within the past million years and still moving with velocities close to their parent star's velocity. Tracing the trajectory backward, calculating where the object was millions of years ago, might identify the star system of origin. This requires precise astrometry, measuring the object's position and velocity to high accuracy, and knowledge of stellar motions in the solar neighborhood. The calculation is complicated by gravitational perturbations from encounters with other stars during the object's interstellar journey, but for young ejecta the perturbations are small. A handful of interstellar objects might be traceable to specific stars, providing direct samples from known systems. Preparation for this era of discovery is already underway. Theoretical models predict the properties of interstellar populations based on simulations of planetary formation and ejection dynamics. Observational strategies optimize telescope time allocation, balancing the need for rapid follow-up with other scientific priorities. Data pipelines are developed to handle the volume of alerts and process spectroscopic data efficiently. International collaborations form to coordinate observations across multiple observatories and time zones. The infrastructure is being built now, anticipating a future in which interstellar objects are discovered regularly. Routinely, no longer rare curiosities, but a new class of astronomical objects studied in detail. Only took a century of technological development from photographic plates to digital detectors to gigapixel cameras to reach the threshold where interstellar visitors become statistically accessible. Or perhaps the threshold was always close, and only the will to build larger surveys was lacking. The galaxy has been sending objects through the solar system for billions of years. Soon, humanity will finally begin to see them in numbers sufficient to understand what they are and where they come from. The census begins, the preparations continue, and somewhere in the Chilean mountains, a telescope waits mirrors polished, cameras tested, software calibrated ready to watch the sky and count the exiles as they pass. Every star system is an engine of exile. The process is not unique to the solar system, not an accident of our particular configuration of planets and orbits. It is universal, an inevitable consequence of how planetary systems form. When a molecular cloud collapses under its own gravity, fragmenting into clumps that will become individual stars. Each clump forms a rotating disk of gas and dust. The rotation prevents all the material from falling directly into the star. Instead, it settles into a flattened structure, the protoplanetary disk, where solid particles collide, stick together, and grow through accretion. Kilometer-sized planetesimals form within a few 100,000 years. These bodies collide, merge, and continue growing. But the process is chaotic. Not everything merges. Not everything survives. Gravitational interactions dominate once bodies reach sufficient size. When two planetesimals pass close to each other, their mutual gravity deflects both trajectories. For equal mass bodies, the deflections are symmetric. For unequal masses, the smaller body is deflected more. When a small body passes near a much larger body, a growing protoplanet, a gas giant, the deflection can be extreme, sending the small body onto a highly elliptical orbit or ejecting it from the system entirely. This process clears the protoplanetary disk of leftover material, reducing the population of planetesimals until only the planets remain, orbiting stably, with perhaps a residual population of asteroids and comets in dynamically stable regions. The Oort cloud, the distant spherical shell of comets surrounding the solar system, is a reservoir of material that was scattered outward but not quite ejected. These comets orbit at distances between a few thousand and 100,000 astronomical units from the Sun, loosely bound by the Sun's gravity, perturbed occasionally by passing stars or galactic tides. The Oort cloud contains trillions of comets, with a total mass estimated a few Earth masses. But this is only the material that remained bound. Models suggest that for every comet in the Oort cloud, 10 or more were ejected completely, achieving velocities exceeding escape velocity, becoming interstellar objects. The ratio varies depending on the assumed mass and orbital parameters of the giant planets, but the general conclusion is consistent. Most scattered material leaves the system. Other star systems undergo similar evolution. Observations of young stars a few million years old, still surrounded by protoplanetary disks, show evidence of giant planets forming at various distances from the star. Some systems have hot Jupiters. Gas giants orbiting very close to the star, likely migrated inward from more distant formation locations. Migration implies scattering. As a giant planet spirals inward through gravitational interactions with the disk or with other planets, it ejects vast amounts of material, clearing a gap in the disk, sending planetesimals inward to be consumed by the star or outward to be ejected into interstellar space. The process is efficient. A single migrating Jupiter-mass planet can eject hundreds of Earth masses of material. Systems with multiple giant planets exhibit even more chaotic dynamics. Resonant interactions between planets can destabilize orbits, leading to close encounters, collisions, or ejections. Some planetary systems eject one of their own planets, a gas giant flung into interstellar space by a gravitational interaction with another planet. These rogue planets, unbound from any star, drift through the galaxy like comets but far more massive. Observations suggest that rogue planets may be as common as stars, though they are difficult to detect because they emit no light and reflect no starlight unless they pass very close to a luminous object. Gravitational microlensing surveys, which detect planets by their gravitational effect on background starlight, have found evidence for a large population of Jupiter-mass rogue planets in the Milky Way. The ejection process does not stop after the first few million years of planetary system evolution. It continues, at a reduced rate, for billions of years. Long-period comets from the Oort cloud occasionally fall inward, perturbed by passing stars, and some of these are ejected by planetary encounters, rather than returning to the Oort cloud. Asteroids in unstable resonances with Jupiter are gradually removed, some falling into the Sun, some colliding with planets, some ejected. Kuiper belt objects, perturbed by Neptune, migrate inward and may be ejected after one or more close encounters with the outer planets. The rate is slow, perhaps a few ejections per million years in the current solar system, but cumulative over billions of years. The total number is substantial. The statistics are staggering when scaled to the galaxy. The Milky Way contains roughly 200 billion stars. Most of these stars have planetary systems, based on exoplanet surveys that find planets around more than half of all Sun-like stars and an even higher fraction around smaller, cooler stars. If each system ejected an average of 10 to 100 Earth masses of material during formation, and if this material fragmented into objects ranging from dust grains to planets, the total number of interstellar objects in the galaxy is measured in the quadrillions or quintillions. Most are small, less than a kilometre across. Some are larger asteroids, comets, dwarf planets. A few are planetary mass, rogue worlds wandering the galaxy without a sun. This population is ancient. The oldest stars in the Milky Way formed more than 12 billion years ago, and their planetary systems ejected material shortly afterward. That material has been drifting through the galaxy for 12 billion years, perturbed occasionally by stellar encounters, slowly dispersing, gradually accumulating in radiation damage and interstellar dust accretion. Younger populations eject from stars that formed a few billion years ago, or a few 100 million years ago, are less weathered, less perturbed, still moving with velocities close to their parent stars. The galaxy contains a superposition of populations from different epochs, different formation environments, different stellar metallicities, all mixed together in interstellar space. indistinguishable except through detailed chemical and dynamical analysis. Only took billions of years of planetary formation, repeated across billions of star systems, to fill the galaxy with exiles numbering beyond comprehension. Or perhaps it happened faster, concentrated in the first few billion years when star formation rates were higher. The galaxy does not keep records of individual objects. It simply accumulates them. The population continues to grow slowly as new stars form and new planets scatter new material, and somewhere in the disk, another planetesimal passes too close to a giant planet, accelerates past escape velocity, and begins a journey that will last until the galaxy itself dissolves, a journey without destination, without purpose, without witness, one exile among quadrillions, contributing its infinitesimal mass to the dark and distributed inventory of the Milky Way. 2I/Borisov continues outward. Perihelion occurred on December 8, 2019 at a distance of 2 astronomical units from the Sun. By March 2020, the comet has crossed the orbit of Jupiter, its coma fading as solar heating decreases and outgassing slows. By mid-2020, it passes beyond Saturn, dimming below the detection threshold of most ground-based telescopes. Hubble Space Telescope continues to track it for a few more months, capturing images as the comet becomes a faint smudge against the background stars, barely distinguishable from distant galaxies. By early 2021, the comet is too faint even for Hubble. The last observations are archived, the data is processed, the papers are published, and 2I/Borisov fades from scientific attention, receding into the outer solar system, unobserved and unobservable. The trajectory does not change. Gravity continues to govern the motion. The comet climbs out of the Sun's gravity well, decelerating as it converts kinetic energy into gravitational potential energy, but never slowing enough to stop, never turning around. The hyperbolic orbit ensures departure. By 2025, the comet crosses the orbit of Neptune, entering the region where the Sun's influence weakens and interstellar space begins. There is no sharp boundary. The solar wind extends far beyond Neptune, gradually thinning, eventually merging with the interstellar medium. The heliopause, the region where solar wind pressure balances interstellar pressure, lies roughly 120 astronomical units from the Sun, varying with the solar cycle and the density of nearby interstellar gas. 2I/Borisov will cross this boundary sometime in the 2030s or 2040s, depending on its exact velocity and trajectory. Beyond the heliopause, the environment changes. Cosmic ray intensity increases because the solar magnetic field no longer deflects low-energy particles. The solar wind disappears, replaced by the tenuous flow of interstellar plasma hydrogen and helium ions, moving at tens of kilometers per second relative to the Sun, driven by pressure gradients in the local interstellar cloud, the bubble of slightly denser gas through which the solar system is currently moving. The temperature of the interstellar medium is a few thousand Kelvin, measured by the thermal motion of ions, but the density is so low, roughly 1 particle per cubic centimeter, that the comet's surface feels no heating. Instead, the surface cools to the ambient radiation temperature, around 3 Kelvin, the temperature of the cosmic microwave background. At this temperature, all volatiles except helium and hydrogen remain frozen. Water ice, carbon monoxide ice, methane, ammonia, all are solid, stable indefinitely. The comet's nucleus, no longer sublimating, becomes inert. The coma vanishes. The dust tail disperses, the particles continuing on independent orbits, slowly spreading out, eventually mixing into the general population of interstellar dust grains. The nucleus itself, now alone, continues outward. A small dark object perhaps a few hundred meters across, perhaps a kilometer, moving at roughly 33 kilometers per second relative to the Sun, slightly slower than its approach velocity because it lost energy rounding the Sun and climbing back out of the gravity well. The trajectory points toward the constellation Telescopium below the ecliptic plane into the southern celestial hemisphere. This direction is arbitrary, a consequence of the comet's incoming velocity and the geometry of its perihelion passage. It does not correspond to any particular star or destination. The comet will not approach another star system for hundreds of thousands or millions of years, depending on the density of stars along its path. The nearest star to the Sun, Proxima Centauri, lies 4.2 light-years away, roughly 270,000 astronomical units, at 33 kilometers per second. Crossing this distance requires 80,000 years. 2A/Borisov is not aimed at Proxima Centauri. It is not aimed at anything. It simply moves in the direction its trajectory happened to carry it after the gravitational deflection by the Sun. Interstellar space is quiet. There are no collisions, no encounters, no events. The comet drifts in darkness, illuminated only by starlight faint, isotropic, insufficient to heat the surface above 3 Kelvin. Cosmic rays continue to bombard the nucleus, ionizing molecules, creating defects in the ice lattice, darkening organic compounds. The process is slow, measured in geological time. A centimeter of surface material accumulates significant radiation damage over 1 million years. 10 million years of exposure turns the outer layer into an amorphous, carbon-rich crust, reddish-brown, similar to the surfaces of Kuiper Belt objects and other long-lived icy bodies. Beneath this crust, the interior remains pristine, unchanged since formation, preserving the original chemistry of the protoplanetary disk where the comet formed 4.5 billion years ago. The nucleus does not tumble, or perhaps it does, rotating slowly, completing one rotation every few hours or days. The angular momentum imparted by outgassing during the perihelion passage when jets of sublimating gas exerted torques on the irregular shape. The rotation gradually slows over millions of years due to internal friction and redistribution of mass, but the timescale is long, and the effect is negligible over the next few million years. The comet spins, unobserved, through the void. Occasionally, very rarely, the comet passes through a denser region of interstellar space, a molecular cloud, a region where gas density increases to hundreds or thousands of particles per cubic centimeter. The drag from this gas is minimal, insufficient to alter the trajectory measurably. But the increased flux of hydrogen and helium atoms striking the surface deposits a thin layer of frostwater ice accreting from the gas phase, molecules sticking to the cold surface. Over millions of years, this accretion might add centimeters or meters of new material, gradually burying the original surface, mixing interstellar ice with the primordial ice from the comet's formation. The process is uncertain. The duration of passage through molecular clouds is unknown. The chemistry of interstellar ice is complex, but the possibility exists, most likely. The comet simply continues. No clouds, no encounters, no perturbations. It drifts for 1 million years, 10 million, 100 million. The galaxy rotates. Stars move in their orbits around the galactic center. The comet's trajectory, initially pointed toward Telescopium, gradually shifts as the sun's motion carries it to different regions of the galaxy. After a few 100 million years, the comet may find itself in a different spiral arm, surrounded by different stars. Though still not close to any of them, after 1 billion years, the Sun will have completed several orbits around the galaxy, and the comet, travelling in a slightly different direction, will be separated from the Sun by thousands of light years, no longer part of the solar neighbourhood, no longer traceable to its brief encounter with this particular star. Only took 4.5 billion years to form, a few million years to travel between stars, a few months to pass through the inner solar system, and now an eternity to continue outward into permanent night. Or perhaps not eternity, perhaps another encounter waits, another star system, another brief warming, another sublimation, another coma. The universe does not promise repetition. It simply allows motion. The trajectory continues. The darkness continues. And somewhere beyond Neptune, a small icy nucleus drifts, silent, unseen, carrying molecules frozen since before the Earth existed, moving through the galaxy without purpose or destination, one object among quadrillions, returning to the void from which it came. Interstellar objects are messengers, but they carry no messages. They are not sent. They are not addressed. They arrive without announcement, depart without farewell, and convey nothing except their physical properties: mass, velocity, composition, shape. These properties encode information, but not in the sense of intentional communication. A comet's chemistry reveals the temperature and pressure where it formed, the elemental abundances in its parent protoplanetary disk, the timeline of its ejection and interstellar journey. This information exists as consequence, not as signal. The comet does not know what it carries, it simply exists, shaped by processes that operated billions of years ago, preserved by cold and vacuum, occasionally perturbed by gravity or radiation, but fundamentally unchanged. The absence of messages is itself informative. If interstellar space were full of artificial probes, beacons, archives, autonomous explorers, some fraction of interstellar objects detected would show signatures of design, regular geometries, unusual material properties, active propulsion, electromagnetic emissions. None of these have been observed. Oumuamua, despite its anomalies, shows no clear evidence of artificiality. 2I/Borisov is unambiguously natural. The population of interstellar objects appears to consist entirely of debris fragments, ejecta, the passive byproducts of planetary formation. This does not prove that artificial objects do not exist. It simply means they are rare enough, or subtle enough, to remain undetected among the natural population. The chemistry of interstellar objects is familiar. Water, carbon monoxide, organic compounds, silicate dust. These are the same materials found in solar system comets, asteroids, and planets. The isotopic ratios vary slightly, reflecting different formation conditions, but they fall within the range of solar system diversity. No exotic molecules, no elements in unexpected proportions, no signatures of processes that do not occur naturally. This familiarity suggests that planet formation proceeds similarly around other stars. The laws of physics are universal. The chemistry of protoplanetary disks is governed by thermodynamics, which operates the same way everywhere. A comet formed around a sun-like star 10 light-years away will resemble a comet formed around the sun because the conditions are similar and the available elements are the same. Yet small differences exist. 2I/Borisov's elevated carbon monoxide abundance suggests formation in a colder environment than typical solar system comets, or at least preservation of CO that would have sublimated away in most solar system objects. This difference is small, within natural variation, but it hints at diversity. Different planetary systems have different temperature structures, different giant planet configurations, different timelines for scattering and ejection. Sampling more interstellar objects will reveal the full range of this diversity, constraining models of how planetary systems form and evolve across different stellar masses, metallicities, and galactic environments. The motion of interstellar objects carries no intent. They do not navigate. They do not adjust trajectories. They follow ballistic paths determined entirely by gravity, the gravity of their parent star at ejection, the gravity of stars they pass during interstellar transit, the gravity of the Sun during their brief passage through the solar system, and the distributed gravity of the galaxy as a whole. The paths are deterministic, calculable from Newton's laws or, for higher precision, Einstein's general relativity, but they are also chaotic in the sense that small perturbations, an encounter with a rogue planet, passage through a molecular cloud, A distant stellar flyby can alter the trajectory in ways that accumulate over millions of years, making long-term prediction impossible. A comet's future cannot be known with certainty. Only its present motion can be measured. The shape of interstellar objects is determined by formation, collisions, and tidal encounters. Oumuamua's elongated shape might result from tidal fragmentation during a close stellar flyby, or from collisional shattering in its parent system, or from structural failure due to internal stresses. 2I/Borisov's shape is unknown because the nucleus remains hidden beneath the coma, but it is probably irregular, like most comets, potato-shaped, cratered, asymmetric, no perfect spheres, no smooth surfaces. Nature does not polish objects, it fractures them, erodes them, accretes material onto them in haphazard layers. The irregularity is a signature of natural processes. The silence of interstellar objects is absolute. They emit no radio waves, no laser pulses, no modulated signals. They reflect sunlight passively, scattering photons according to their surface properties. They absorb heat and re-radiate it as thermal infrared, at wavelengths determined by temperature. These emissions are predictable, explainable by blackbody radiation and scattering theory. There is no component that requires intelligence to explain. The objects are inert. In the thermodynamic sense, they contain no internal energy source, no active processes except sublimation when heated by a star. They do not think, they do not act, they simply move. This silence extends to the broader question of galactic communication. If intelligent civilizations exist and attempt to communicate across interstellar distances, they might use physical artifacts as well as electromagnetic signals. A probe sent to a star system could carry information encoded in its structure, its materials, or its behavior. An artifact orbiting in a detectable location near a star's habitable zone, for instance, might signal its presence through unusual reflectivity or orbital characteristics. The absence of such artifacts among the thousands of asteroids and comets already catalogued in the solar system suggests either that no one has sent them, or they are too rare to have been detected yet, or they are present but unrecognized because they resemble natural objects too closely. Interstellar objects are samples, not signals. They provide physical evidence of processes occurring in other planetary systems, but they do not convey intent or information in the communicative sense. A geologist studying a rock does not expect the rock to explain its history. The history is inferred from isotopic ratios, crystal structure, mineral composition properties that record the conditions under which the rock formed. Similarly, astronomers studying interstellar objects infer the history of the objects from their chemistry, dynamics, and physical properties. The objects are data, not messages. They exist to be measured, not to be read. Only took billions of years for the galaxy to produce quadrillions of these samples, scattering them through interstellar space, and a few thousand years of human civilization to develop instruments capable of detecting and analyzing them. Or perhaps it took longer, hundreds of thousands of years of human evolution, millions of years of primate evolution, billions of years of biological evolution on Earth, all as prerequisite to the existence of observers capable of noticing a faint speck moving against the background stars and recognizing it as something from elsewhere. The universe does not produce observers intentionally. It simply allows complexity to emerge where conditions permit. The observers notice. The objects pass. And somewhere in the data, a spectrum waits absorption lines, emission lines, continuum slopes, evidence of chemistry and motion and time, written in wavelengths, preserved in archives, carrying no message except the fact of existence, which is perhaps enough. The comet recedes. Each day it is farther from the sun than the day before. Each year it crosses another orbit, Uranus, Neptune. Eventually the scattered disk where trans-Neptunian objects drift in slow ellipses. The sunlight dims. At 50 astronomical units, the sun appears as a bright star, brighter than any other but no longer a disk, no longer warm. At 100 astronomical units, the sun is merely one point among thousands, distinguishable only by its brilliance. At 200, 300, 1,000 astronomical units, the distinction fades. The sun becomes part of the stellar background, one light among multitudes, and the comet moves through darkness that is not quite absolute but close enough that the difference no longer matters. The nucleus does not change. Ice remains ice. Dust remains dust. The molecules locked in the lattice water, carbon monoxide, methane, ammonia stay frozen, stable at 3 Kelvin, the ambient temperature of the universe. There is no decay, no erosion except the slow accumulation of radiation damage, which proceeds at a pace measured in millions of years. For now, for the next 1,000 years, the next 10,000, the comet is simply what it is, a small body of ice and rock, moving, silent, dark. The trajectory carries it away from the ecliptic plane, downward into the southern celestial hemisphere, toward regions of space the sun will never visit. The distance grows, 1 light year, 2, 4, 10. The numbers become abstract, too large to visualize, measured in units that have meaning only as ratios. The comet does not measure distance, it moves, and the motion continues, governed by momentum and the faint pull of distant stars. Too weak to deflect the path, but present nonetheless. A reminder that gravity never entirely vanishes. Somewhere in the galaxy, other comets drift. Trillions of them. Quadrillions, perhaps. Each on its own trajectory, each carrying its own history encoded in chemistry and shape. They do not interact. They do not collide. Space is too vast, the density too low. They pass within light years of each other, unaware, unseen, each alone in the void. The galaxy is full and empty at once, full of matter, empty of events. The stars continue their slow rotation around the galactic center. The sun moves, the comet moves, the distance between them grows until the distinction between motion and stillness becomes meaningless. Both are moving, both are still. The galaxy turns, and within it, everything drifts. The comet does not know where it is going. It has no destination. It will arrive nowhere because there is nowhere to arrive. It will continue until the galaxy itself disperses, until the stars burn out, until the universe cools to a state where even the cosmic microwave background fades to nothing. Or it will encounter another star, be captured briefly, perturbed, released again. Or it will collide with something, a rogue planet, another comet, a dust cloud dense enough to erode the surface. The future is open, unwritten, indeterminate. For now, it simply moves. The ice remains frozen. The surface remains dark. The molecules remain bound. And in the silence of interstellar space, time passes without event, without change, without witness, a stillness so profound that motion itself becomes a form of rest. The universe does not pause, it continues. The comet continues. The darkness continues. And somewhere, far behind, a small blue planet orbits a yellow star, and on that planet, observers archive data, write papers, build telescopes, and wait for the next visitor to arrive, knowing now that the galaxy is full of them, that the void is not empty, that the silence is populated with exiles beyond counting, all of them drifting, all of them alone, all of them moving through the same quiet darkness into which 2I/Borisov now fades unreachable, unobservable, gone.